we've got block A sitting on a table with friction. We've got block B hanging from that table and not touching the wall, so no friction on B. And we need to know here if the blocks move and then how fast or what is their acceleration. Now, we know here, so based on these numbers that are given to us, B weighs less than A. So is B going to be able to pull A? It depends on how much friction is on that table. If B will be heavy enough to overcome it. So we'll have to do the static check. And then after that, we'll be able to see if the blocks move and then how fast. So here we need a free body diagram for each block. So we'll start out with, here is block A. And then actually, let's say part C, tension and rope. That's another good one to find. Okay, so for A, we've got the weight of A, MAG, pushing down, and we've got the normal force pushing up. Then we also have friction trying to keep A from sliding. And then we've got the tension here that's trying to pull A. And the coordinate frame here for A has X in the direction of motion and Y perpendicular. And then the coordinate frame for B, we have to make X follow the rope. So for B, we'll have X here in the direction of motion, and we'll have Y perpendicular. So for B, we don't put the Y direction vertical because we need to make X follow the rope. And this is important because when we write the free body diagram equations, those X and Y force equations for each block, we're assuming that the X direction is what's going to have acceleration. So B accelerates in X, A accelerates in X. So that's why we just make X follow the rope, and then all the equations will work out nicely. So now here from B, not as many forces. We have the weight of B going down, and we have the tension in that rope going up. Okay, so now we have to write the equations for each block. So for block A, we'll have sum of the forces on A and the Y equals 0. And so we have the normal force pointing up, MAG pointing down, and this gives us that normal force equals mass of A times gravity. So normal force is 196.2 newtons because that would be the 20 kilograms times 9.81. And then from there we can get friction force. So static friction equals static coefficient times normal force. So we have 0.7 times 196 equals 137.3 newtons. And then the dynamic friction equals, well, really this is what we called it kinetic. Kinetic and dynamic are the same thing. UK times normal force equals 0.5 times 196. This equals 8.1 newtons. So then so we got that for A. And then the sum of the forces on A and the X equals mass of block A times acceleration. And in that case, we have tension pulling to the right minus friction force on A. And then we need to write for B. So for B, we'll have sum of the forces in X equals mass of B times G minus tension equals MB A. because again, we're writing, remember, B has X going down and Y going perpendicular. And so we're assuming motion in the positive X direction. Therefore, down is going to have the positive value here because we're assuming that positive acceleration is down and to the right. And we have the tension holding it back. Now, tension is not necessarily equal to the weight of the hanging block. It will only be equal to the weight of the hanging block if the blocks do not move. If the blocks do move, tension is not equal to that weight. So that's why we can't just automatically write down the tension. All right, so now we're trying to figure out what is the acceleration of the blocks and the tension in the rope. So we've got the X equations for B. We just got those from our sum of the forces in X on B. So massive B times G minus tension equals massive B times A. And then from the A equations in the X direction, we have massive A times acceleration equals tension minus friction. And this is going to be the dynamic friction because now that we know the blocks are moving. So we have two equations and two unknowns, and we can solve this. So the easiest way here is to solve by elimination. You can do substitution, where you rearrange one equation and solve for T and plug into the other one and solve for A. Or you can do elimination, where you just stack these two equations and add them together. So if we add these two together, these T's are going to cancel. And then we're going to get massive B plus mass of A times acceleration equals massive B times G minus dynamic friction. And then we rearrange and get A equals massive B times G minus dynamic friction over the total mass, MA plus MB. And so if we plug numbers in here, we have MBG, which actually we found that here, 147.15, minus the dynamic friction, which we got here, 98.1, over the total masses, 20 plus 15. So we put this into a calculator, and we get that A equals 1.4 meters per second squared. So that is positive, which is a good thing, because we assumed that B was going to move down and A was going to move to the right. And also, it is a pretty small value. And we can see that the friction is high and B weighs less than A. So that does make sense that it should be small. Now to solve out for tension, we will take one of these equations, either equation, doesn't really matter which, but we'll take this equation here and solve for tension. So we move T to the other side, and then we move MBA to the right, and we'll have T equals MBG minus MBA. And so this is going to be the mass of B is 15 times G, which is 9.81, minus A, which we just got, is 1.4. And so T equals 126 newtons. So we can see that T is less than the weight, because it would be, this is a subtraction here. And that makes sense. There should be less tension. T should be less than the weight of B if the blocks are accelerating downwards. Because the rope is basically holding B back, but not enough, because B is still going down. If B were accelerating up, which for whatever reason, if maybe A was a car that had an engine on it and it's trying to tow B upwards, in that case, tension should be greater than the weight of B, because B is going up. We'll look at a simulation of this. So here in MATLAB, I have put in the weight or mass of A and B, the static and the dynamic friction, acceleration due to gravity, and I have a check to see if the blocks slide and what is the acceleration if they do. So we run that. So we can see there that the blocks do slide, and also here's their position. Position of A increasing to the right, position of B going down, and this position versus time is parabolic. And that makes sense too, because if acceleration is a constant, then velocity is linearly increasing, and position should be quadratic, like a t squared, basically. So that should make sense for this. And the benefit to doing this simulation here is, what if we could change something? So let's say, what if we make friction 0.8 and then we run this? Then it tells us, so we get an error there. Blocks do not slide, too much friction. So if you can program something like this, like just for future at your job, if you need to do calculations like that, if you put it in a program, then you can just very easily just change those numbers and see what works and what doesn't, without having to put it all in your calculator over again.